Okay, let's go through the radioactive decay and nuclear energy worksheet. The purpose of this worksheet is first to help us understand the concept of a half-life. That is the time scale that we use to understand how fast a radioactive element decays. And a radioactive element is some element whose nucleus of the atoms of that element are unstable and they break apart. And they do so in a sort of probabilistic way. So they don't have an internal clock and they like say, oh, okay, 1 year has passed, I'm now going to decay. We have to look at a large ensemble of atoms, and after a certain period of time, on average, half of them will have decayed, but the other half won't. So the same amount of time has passed, half will have decayed, the other half won't. Think back to the demonstration that we did with flipping pennies in class. So our first question takes a look at uranium-238. The half-life of uranium-238 is 4.5 billion years. The question just says, if we have a chunk of pure uranium-238 that was pure when the Earth formed 4.5 billion years ago, what fraction of it would have decayed into thorium-234 today, 4.5 billion years later? So for this particular question, it's just looking at the definition of half-life. By definition, 4.5 billion years for this particular element is one half-life. That means exactly half of it will have decayed. Since it decays into thorium-234, that means half of this original uranium-238 will have decayed into thorium-234 after 4.5 billion years. So our answer is just a half. Now, the next part of the problem says, let's go for more than one half-life. And we're going to take a look at a different element and its decay, and it has a different half-life. So uranium-235, which is a different isotope of uranium, it has 3 fewer neutrons in the nucleus. It decays into cesium-135 and other things. And it does so with a half-life of 2.3 million years. What we're going to do now is start with uranium-235. Cesium-135 itself is radioactive, has a half-life of 2.3 million years. We're going to fill out the table and go through the half-lives and see how much of that original cesium-135 is remaining. So cesium-135 is radioactive. It has a half-life of 2.3 million years. We're not actually even worried about the precise number of years in the half-life for this exercise. So after 0 half-lives, that means 0 time, 100% of my cesium-135 is still cesium-135. After 1 half-life, by definition, half of it has decayed. So I'll have 50% remaining after 1 half-life. After 2 half-lives, that's 1 more half-life after the first one. Half of my original cesium has already decayed. The remaining half, now, half of that decays. So that only leaves me with 25% of the original. And a way to look at that is we can say, let me start with a chunk of cesium-135 that's pure. After 1 half-life, if I go in and sort it so that I've got the undecayed stuff and the stuff that has decayed on different sides of my block, after 1 half-life, I would have 1 half that is decayed and 1 half that's still cesium-135. This stuff is now cesium-135. It's half of the original. After 1 more half-life, half of that will have decayed. So that's now after 2 half-lives. The hash marks are indicating what's decayed. So now 75% is decayed, which means 25% after 2 half-lives has not decayed, and that's the fraction that remains. After 1 more half-life, half of that 25% decays. What's remaining then is half of 25%, or 12.5%. That's the bit in this little corner here. After one more half-life, half of this little 12.5% piece decays, so that only 6.25% is remaining. That's this little bit now in this corner. Of course, when it's decaying, it doesn't actually organize itself into that corners that way. It's randomly distributed throughout the block, but this helps us count. After the fifth half-life, half of that part decays. Half of 6.25 is 3.125%. So after 5 half-lives, this little bit here is the 3.125% of the original that's remaining. So what do we notice? Half-life may make us think that if half decays after 1 half-life, all of it will have decayed after 2, but that's not the way it works. This stuff doesn't remember that it went through a half-life and didn't decay, just like when you flip your coin, and we were doing that demo in the class, the second time you flip the penny, it doesn't care that the first time it came up heads. It just is going to do its 50% thing each time. So these numbers never actually really go all the way to 0, although if we wait long enough, it'll get very, very close to 0. Now, the final part for this question, take a look at the numbers we put in the table above, and can we come up with an equation that would help us get how much is remaining without going through this sort of table step. So the hint says, notice that 0.5 raised to the power of 0 is 1, which is 100%. And 0.5 raised to the first power is 0.5, which is 50%. And we can now see a pattern that 0 being the exponent gives me the value in the right-hand column. 1 being the exponent that the base 0.5 is raised to gives me the answer of 50%. So 0.5 raised to the nth power is the percent remaining after n half-lives. Now, the second part of this worksheet asks us to compare the energy density, basically, of a fossil fuel. We pick coal as an example. We get about the same numbers if we were using natural gas or oil, compared to the energy in uranium, the nuclear potential energy available in uranium. And we start this just by taking a look at how much energy we need as Americans for electricity. So the average American consumes about 30 kilowatt hours of electrical energy at home each day. The total chemical potential energy in 1 kilogram of coal is 8 kilowatt hours. So since this number is smaller than this number, I know I'm going to need several kilograms of coal to get my energy need, more than 1. However, if I'm getting electricity from coal, I'm burning it in some fossil fuel power plant, and that's subject to the second law of thermodynamics, so it can't be 100% efficient. So let's assume that that coal power plant is 33% efficient. How many kilograms of coal do you as an American need each day in order to get 30 kilowatt hours of electrical energy? Well, there's a couple of different ways we can look at this. One way would be to say, okay, how much energy do I actually get from a kilogram of coal? So the electricity from 1 kilogram of coal is going to be equal to 8 kilowatt hours times 0.33. Only 33% of that 8 kilowatt hours is actually converted into electricity. How do I know it's times and not divide? How do I know how to multiply and not divide? Because the efficiency is less than 100%, I get less than this much energy. This is how much total energy there is in the coal. I only get 33% of it, so I'm going to end up with a smaller number than 8. That means I have to multiply by 0.33. 8 times 0.33 gives me 2.64 So I get 2.64 kilowatt hours of electricity per kilogram of coal, not 8. That then lets me figure out how much coal is needed to give me 30 kilowatt hours. So the number of kilograms of coal needed for 1 American is 30 kilowatt hours divided by 2.64 kilowatt hours per kilogram, and that gives me 11.4 kilograms. That's for 1 American for 1 day, okay, because that's my 30 kilowatt hours per day. How do I know in this case to divide instead of multiply? Well, I can figure it out from the units. As you can see here, the kilowatt hours cancel. I have kilograms in the denominator of the denominator. That'll bring it up and give me an answer of kilograms. If I had multiplied, I would end up with kilowatt hours squared per kilogram, which is a confusing thing that doesn't mean anything. The other way to look at it, figure out whether I multiply or divide, is just to think about, do I need more than 1 kilogram or less than 1 kilogram of coal to give me 30 kilowatt hours? 1 kilogram gives me 2.6. 2 kilograms would give me twice that, 5.2. I need 30. So I need to have a lot of kilograms to get from 2.64 up to 30. So if I divide 30 by 2.64, that tells me the number of kilograms I'm going to get. If this 2.64 were a bigger number, suppose it were 30, how many kilograms would I need? Just 1, right? I would get that 1 by dividing 30 by that 30. If I multiplied, I would get 900. That wouldn't make sense. It would say that the more energy there is per kilogram of coal, the more coal I need, but I need less kilograms of coal the bigger this number is, so this number's got to be in the denominator. The second part of the question says how much coal would be needed to supply the electricity for 1 American for 1 year. So for 1 year, we just multiply this number by 365 days. So it's 11.4 kilograms per day times, running out of space here, times 365 days per year. And the days cancel. I'll end up with kilograms per year, and the answer is 4,150, rounding up a little bit, kilograms per year. So that's how much energy, that's how many, kilograms of coal are needed to supply the average American's electricity for 1 year. 1 kilogram of uranium-235 has a lot more energy than a kilogram of coal. Kilogram of coal, 8 kilowatt hours. Kilogram of uranium, 24 million kilowatt hours. So I know that I should get a much smaller amount of uranium ultimately needed to provide my electricity. Well, the first part of this question just says natural uranium, or only 0.7% of it is the good stuff that we use in a nuclear reactor. So how much energy comes from a kilogram of ore? If I only get 0.7% of it giving me energy, then the energy from the ore is equal to 24 million times 0.7%, that's 0.007, and that is 168,000 kilowatt hours. This is in kilowatt hours. I'm just multiplying by efficiency here. So if we got all of our nuclear fission, all of our electrical energy from this source, and the plant, again, just has a 33% efficiency, how many kilograms of unenriched natural uranium would need to be mined, transported, etc., to supply my consumption for 1 year? Well, how much energy needed by an American for 1 year is 30 kilowatt hours per day times 365 days per year. 30 times 365 is 10,950 kilowatt hours per year. That's how much electrical energy the average American uses at home per year. How many kilograms of unenriched uranium is needed to provide that? Well, how much energy do I get from a kilogram? The energy available in the ore is our answer from part B. It's 168,000 kilowatt hours, but I have to put this in a power plant that's only 33% efficient. So the energy that I get is 168,000 kilowatt hours per kilogram times 0.33. That's that efficiency again. I get less energy than that because it's not a perfectly efficient plant. 168,000 times 0.33 gives me 55,440 kilowatt hours per kilogram. So that's how much energy actually makes it to my house from each kilogram of raw ore. I started with 24 million kilowatt hours of energy if I had pure uranium-235, but the ore is only 0.7%, so that knocks it down to 168,000. The power plant is only 33% efficient, so that knocks it down to 55,000, but I need 10,950. 1 kilogram supplies more than 50,000. So that tells me I need less than a kilogram of uranium ore to provide that electricity. So the amount needed, the amount of ore needed, I'm going to do the same operation I did up here. I'm going to take my needed amount of energy, 10,950 kilowatt hours per year, divided by 55,440 kilowatt hours per kilogram. The kilowatt hours are going to cancel because this is in the denominator of the denominator. It goes up into the numerator, and that'll give me kilograms per year. That's what I'm looking for. And the number, 10,950 divided by 55,440 is 0.2, rounding. It's 0.1975 kilograms per year. Compare that to the 4,000 kilograms per year of coal needed. It's a factor of about 20,000. We had been working with a factor of about 10,000 difference in the energy density between coal and nuclear fuels.